All right, let's go ahead and look at those kinematic equations we derived last time. We found for x direction that x at any time is initial x position plus the initial velocity in the x direction times time plus 1/2 acceleration, the x direction times the square of the time. And the same thing in the y direction, except x is replaced with y. All right, we're going to go practice using these equations. Probably the most important application of these is what we call projectile motion. So if I shoot something up in the air, where does it go? And there's one thing that we have to figure out before we address these problems, and that's what the acceleration in the y direction is when it's acted on by gravity. So imagine I have a ground here, and I have some object above the ground, and gravity is pulling it back down. It's a little out of sequence, perhaps, because we might want to do forces first before we do the acceleration due to gravity. But it's important to have what the acceleration due to gravity is. Well, it turns out that any object that's acted on just by gravity above the surface of the Earth will accelerate downwards with the same acceleration, and it would accelerate downwards with an acceleration in the y direction equal to what we call negative g, if provided y goes upwards. And g is 9.8 meters per second squared. You will see the book tell you 9.81. That's probably true somewhere on Earth. But I asked the geoscience people about this, and at Hays, Kansas, they have these fancy gravitometers that they use to actually figure out the local gravitational acceleration to like 10 decimal places. And they use this to look at density of rocks, and then they can find oil that way, you know. Well, I don't know, you probably know more about it than I do. They have these fancy measurers of the gravitational acceleration, and to 1 decimal place, it's 9.80, you know, the 2 decimal places. So 9.8 is good for Hays. Okay. And so the acceleration in the y direction is, if y is pointing up vertically, it would be negative 9.8 meters per second squared.
Why is it negative?
Because it's accelerating downwards towards the ground. So the component of acceleration in the y direction is in the negative y direction.
And just since you put.
And that's our gravitational pull, right?
This is the acceleration due to gravity. That's not the gravitational force, that's the acceleration due to gravity of any object. And every object should accelerate the same. If it was a vacuum, that would be the case. However, you know, due to air resistance, it looks like a feather accelerates a lot less than a rock. But if you put it in a vacuum, it would. Yeah, I can get some videos of that. All right, well, let's go ahead and apply this y equation. So first off, we'll do a problem which you've already seen in lab. Let's say I have a ball that I'm dropping from some height h. I'm dropping it from rest. Let's see how long it takes to hit the ground. How long does drop ball take to hit the ground? Well, if it's just dropping, there's no acceleration in the x direction. Only acceleration is gravity. And so we just have to look at the y kinematic equation. So I'm going to start out with this equation here. So y at the time, that's the height above the ground. So I'm going to say this is y equals 0 at the ground, and y points upwards. The y position at any time will be equal to the initial y position plus the initial velocity in the y direction, and then our acceleration due to gravity was in the y direction is minus g, so minus 1/2 g squared. What was my initial position? The height. And what's my initial velocity if I drop it?
0.
Good. So I'd get y at t is equal to h minus 1/2 gt squared. If I'm interested in the time it takes to hit the ground, I'm interested in when y is going to be 0, when it's at the ground. That makes sense? So in this case, I'm going to plug in 0 here. H minus 1/2 g t squared. If I want to solve for this time, what should I do? I'll bring this minus 1/2 gt squared, I'll add that to both sides of the equation. So I get 1/2 g t squared is equal to h. Multiply both sides by 2. Divide both sides by g. G's cancel, 2's cancel, and I get t squared is 2h over g. Now what should I do? Take square root of both sides. So t is plus or minus square root of 2h over g. That minus sign, not physical. It takes a positive amount of time for it to fall down. So we'll just write it like that. And you derived that in the first lab. All right, let's go a little bit more complicated.
So, oh, never mind.
Well, that should be the negative and the 1/2 gt squared. Oh, it's going down.
So right here, because the acceleration in the y direction was negative g. Good. Let's do the next thing. Let's say I throw the ball up or shoot the ball up from the ground, some initial speed v naught. We all, from experience, we know the ball would go up, turn around, and come back down. Right, if I throw a ball up, it'll come up, it'll go up and come back down.
Yeah.
Let's figure out the time it takes to come back to the ground. Okay? Now, how long does it take, does thrown ball take to hit the ground? So again, this will be an application of this kinematic equation. We only have movement in the y direction. We haven't added any x movement to it. It doesn't really matter since even if there was x movement, we're interested in when it hits the ground. That's the y position. That's determined only by y. So let's use this kinematic equation again. So y at any time is equal to the initial y position plus the initial velocity in the y direction. The acceleration, because it's acted on only by gravity. Once it has this velocity and you let it go, it's just gravity that acts on it. Minus 1/2 gt squared. So what's the initial y position if it starts at the ground? And I'm interested in the time when it's back on the ground, right? So I plug in y at the time that I'm interested in to be 0. Follow?
Why is it minus again?
Because, why is it minus g here? Because the acceleration in the y direction is
Yeah,
minus
yeah.
g.
It's going to be,
What were you going to say?
So
Alice?
you're dealing with negative gravity, pulling it down as you're throwing it up, but it's accelerating as it comes down, so it's
It's accelerating constant the whole time. Even when it's going upwards, it's accelerating in the negative.
slowing it
Y
down when
direction.
it's speeding it up.
So we're missing two variables, so how are we supposed to figure it out?
So this v, that was the initial speed, right? So I put this, I just call this v naught,
Okay.
and then that's all I have. I just plug in these things now. So I get 0 is equal to 0 plus this, so I'd write v naught t minus 1/2 g t squared. I'm going to add this plus 1/2 gt squared to both sides of the equation. So I get 1/2 g t squared, initial velocity t. I'm going to notice there's a t and a t squared here, no other terms. So I'm going to divide both sides by t. So if I divide both sides by t, I cancel out that t and cancel out one of these t's. You see that?
Mm-hmm.
So I would get 1/2 g times t is the initial velocity. So if I want to get t by itself, I'm interested in the time. What should I do?
Divide by g and then
Multiply
multiply by g.
So if I do like that, this 2 would cancel that 1/2, that would cancel with the g, and I get that the time is 2 v naught over g. So for instance, if I threw a baseball at 70 miles an hour, or could throw a baseball at 70 miles an hour straight up into the air, you know, you'd get about 30 meters per second initial speed. And the time it would take to come back down would be 2 times 30 meters per second divided by 9.8 meters per second squared. So that'd be 60 divided by this, would be on the that'd be a little under 6 seconds, right? So you could throw a baseball up like that, you'd expect it to come back down about a little over 6 seconds later. Make sense?
Mm-hmm.
All right.
So we would just have to leave T as to the over G, over 9.8, right? Or
Yes.
we would simplify it, but we don't have the initial.
Well, if that would be part of the problem.
So they would give us that,
Yeah.
and yes, okay, sure.
Or maybe you know this time and you want to figure out what the initial is.
Okay.
You can do that too.
So what if the time it goes up and what if the time it goes down?
Well, we haven't solved for that part. We just checked the time to get back to the ground from starting at the ground.
Like from starting at the ground.
So where did you get your 60 meters per second?
2 times 10.
That's
That
what
was just an
RDO was.
example. A little example. All right. Let's say you wanted to see how high a ball thrown from the ground would get to. That's kind of an interesting problem, right? If I throw it up at 30 meters per second, how far above the ground will it get to before it turns around? Yeah, what's the peak?
So the height.
Or the height? That one, what's happening when it gets up to the top, the highest point that it's going to get to?
It stops.
Velocity is 0.
Velocity in the y direction is 0,
Mm-hmm.
right? So that's very good. It
It
stops.
doesn't say that.
So highest point, let's say, what's highest point? Question mark? So the condition for the highest point is that the velocity in the y direction is 0. That means it's turned around, coming back down. So we know that there's a relation between acceleration in the y direction and velocity, right? So the velocity in the y direction is the initial velocity in the y direction plus the acceleration in the y direction times time. This is how we defined actually acceleration, since final velocity minus initial velocity over time was acceleration.
So we don't even have to use
It
the,
would look like that.
so we don't have to use the YT equation at all?
You will have to,
Oh, we will.
but not to get the time. This equation is what's going to give us the time that it takes to get to the highest point.
Okay.
It won't tell us how high it got. It just tells us how long it took to get there.
And then we plug in that to get it.
Once we have this time to get to the highest point, then this y equation will tell you where its position at that time. Does that make sense?
Yes.
Good. So what's this acceleration in the y direction again?
Negative.
Negative g. Good. Negative 9.8 meters per second. By the way, if you were on the moon, you'd have the same equation. This g would just have a different numerical value. If you were on Jupiter, it'd be different, you know, but it's the same. It would look like the same equation, except for this being different. Okay. So let's go ahead and we want to solve for when Vy is 0. That's the condition for the highest point when it's turning around. So I plug in 0 here. Vy minus Vt.
Well, 0.
You add it.
Is it?
So what should I do?
Add.
Add this Gt to both sides.
Mhm.
So I get Gt is equal to the initial velocity in the y direction, or the time, the initial velocity in the y direction divided by g. Hopefully that's clear how I did that step.
Mhm.
This would be the time to get to the highest point. Notice that it is 1/2 the time it took to go up and come back down. So it's exactly like what you were saying, half the time it's going up, half the time it's coming back down. Okay? So if I want to figure out how high it is at that point, what I'll do is I'll just plug it into this equation. I'll say y at that time, which would be the highest point, would be the initial Y position, which was 0, right? If I started at the ground. Plus the initial velocity in the Y direction, times the time, minus 1/2 t squared. I'm going to plug in this time. I can go ahead and do that. Just plug in that time here. So Y max, I'm going to call this Y max, the highest point it gets to. It's going to be initial velocity in the Y direction times that time. That's initial velocity in the Y direction divided by g. Minus 1/2 g times that time squared, which is initial velocity in the Y direction squared over g squared. I can cancel out one of those g's. This is initial velocity in the Y direction squared divided by g. Minus 1/2 the same thing. So if I have 1 of something minus 1/2 of that thing, that this would be half of that thing, right? So this would be 1/2 over g. So the highest point it'll get to is that. And you could plug in any numbers you wanted. By the way, there's a lot of equations that I'm deriving. Each problem may want a different equation. So I'm not interested in having you guys memorize all these different things that I'm getting up here and here and all that. They all come from an understanding of the problem and this one equation. Plus, I guess what's the relation between acceleration and velocity. So you should only hopefully you'll only remember this, and only remember this, and then you'll be able to understand the problem and work with those to get everything else you need.
Okay.
Okay, and not memorize a million different equations for specific problems. Well, you have to really acceleration and velocity.
I'm on.
A what?
They call me masochist, but I'm actually sorry. I don't know really.
Yeah.
Turn that off, hit that little red button.
Oh, the red button?